అదే నీకు Okay, I'll start in a couple of minutes. Okay, so let me start. So last week, we saw explicit state algorithms, model checking algorithms for model checking CTL logic, specifically the CTL operators EU and EG. And we were restricting ourselves to EU and EG and EX, since all the rest of the CTL operators could be implemented in terms of these two operators and the three operators. So those algorithms, so just to very briefly summarize, they were called explicit state model checking algorithms because they they analyzed the transition graph of the Kripke model explicitly, okay, by traversing the transition graph. The algorithms primarily involved in identifying maximal strongly connected components in the graph and then checking paths leading from various states to one of the strongly connected components, and then checking that the desired properties all held good on those paths. So what we will be doing today, I briefly mentioned fairness. It's a couple of times we have seen what the issues there are, and had indicated that I'll later be talking about how to incorporate the fairness constraints into the model checking algorithm, specifically what kind of modifications to the algorithm, the explicit state model checking algorithm that we went through. And that's what I'll be doing today as the first part of today's lecture. That should take about 15 to 20 minutes. After that, I'll be making transition to introducing symbolic model checking procedures for TTL operators. So this is the plan for today. Oh, shoot. I have to start recording. I can see only if I stop sharing. Stop share. And recording. This is okay. So you're back. Good. So fairness and CTL. This is a recap. As you know, fairness is expressed by defining a fair Kripke structure by adding to the Kripke model a fairness set F constraints, fairness constraints. That's actually a set of states as fairness constraint, and a path in the Kripke structure pi is defined to be fair with respect to the fairness constraint F if and only if for every constraint pi in F, any one state in pi must occur infinitely often. Any one of those states in these P1 in a pi must occur, but for it has to happen for each of those sets. Well, path is yeah, that's how it is now. So as we know, all paths end in a yeah. So where is it? Yeah, I mean, okay. This can, since every path in a Kripke structure will have to, because these are infinite paths, and the only way you can have infinite paths in a finite state system is that that path is a prefix to some thing which ends in a strongly connected component. Therefore, this fairness can also be described. This condition can be viewed as a path ending up in an SCC, and the only way that these states can occur infinitely often is, so then we express this in terms of an SCC being fair. An SCC is fair if one of the the states on the strongly connected component is from a PI. Okay, for each of these PIs, one of the states in that state must occur inside, must be one of the states inside the SCC. Okay, so then by construction you can see that that the path, such a path, will be fair, and that's what we will use. So this idea is what we will use to modify the model checking for EG to take care of this, okay, and EU. So just once again, a background about why we'll have to do this in a special way for CTL. See, in LTL, the fair satisfaction, which is defined as satisfaction relation. Fair satisfaction can be defined as within LTL itself. Okay, so a fair path is expected to satisfy. Yeah, a path is satisfies phi and only if that path has to be fair. If it is fair, only it has to be satisfied only on fair paths, which can be expressed as an implication. Since yes, so this can directly be expressed in LTL. And so there's no issue there. So checking only for a subset of the paths that are fair can be expressed itself as in terms of the standard satisfaction relation for LTL. Now, since CTL, such a thing is not possible because this implication itself cannot be expressed in CT, is not a CTL formula, a well-formed CTL formula. You will have to take care of that either do model checking, which means that you'll have to build it into the formal semantics, and that's what we will first define. We'll first define, we'll see how to modify the standard semantics of the CTL operators to that those things being satisfied on a subset of the paths. Okay, so here for your recollection, the standard semantics was described in this way. So for each of these operators, so since a CTL formula is a state formula at the top level and at every hierarchical level, it is defined, and at the atomic level, if it is a atomic predicate P, then it is true in a state okay, for a given model. If P is true of that state, Ex of some CTL formula F is true in a state, there is a path from pi from that state such that in the next state, F is true. Okay? The formula F has to be true in the next state, not the first one, but the next one. Okay? So I am assuming that the pi 1 denotes the state at index 1 on the path pi. So EG of F is true if and only if there exists a path pi from the state such that for every state on that path, the subformula F has to be true in that state. And EF1 until F2 is true if and only if there exists a path pi originating from the state S, such that there exists a future state K greater than or equal to 0 at some point, at which the second argument F2, the formula that appears second argument, is true and that state. And starting from the first state on the path pi up until to the point where F2, to the point before F2 becomes true, F1 must hold good in all the states, must continuously hold good. That is, it must hold good in all, in every state from 0 to the point prior to the state in which F2 holds good. Now, I mean, as you would see, the formal, so these things are modified for fair satisfaction. So this with an F, suffix F here, what it means is that a formula F is expected to, I mean, yeah, so it defines this as what it means for a formula, CTL formula, to be satisfied under the fair semantics. So if it's an atomic predicate, then, you know, so the intuition is this is going to be defined such that, you know, it is it is enough to be satisfied, a formula, if on all fair parts from the state. And that's how it is defined. Since a predicate is satisfied right in the first state and is not dependent on any path, so it is defined the same way as in standard semantics. So it is satisfied if it is satisfied in the first state. Now here's where the difference start emerging. So Ex of F is true under fair semantics, when only there exists a fair path pi from S such that F is true in the second state from the first state, okay? From the following, from the following state. Note the importance here, there exists a fair path, okay, from pi. So it is required to be satisfied only on all fair paths originating from that. So the subtle difference here will be that if there is no fair paths at all originating from S, this becomes vacuously true, okay? And that makes up, that you have to make note of, and that makes a big difference in the way that you need to understand satisfaction under fairness. Yeah, so EG of F is true under fair semantics if there exists, once again, a fair path originating from that state, such that for every state on that path, F has to hold good fairly. Okay.
Could you repeat why you said it vacuously holds true? I somewhat lost you there.
Yeah. So what does that mean? Existential quantification. Suppose, I'm sorry, no. It's vacuously false because there is no if there's, what it says is there must, look at the way it is defined, there must exist a fair path on that state. So it's vacuously false. Did I say true? Then it's wrong, okay? What I said was if there is no fair path at all, then it is vacuously false, okay? Did I say true? If I said true, then that was wrong. If there is no fair path at all, that's how existential semantics is defined, okay? So if there's no fair path at all, then it's because it includes the constraint that there exists a fair path, okay? And on that fair path, it has to hold good, okay? So that's how it is defined, yeah? So from that state, if there are no fair paths, then because of the existential, to preserve the existential semantics, it is considered to be false. Yeah. And G of f is true if there exists a fair path pi from S such that, yeah, on each of those states, for all I, this thing has to be, yeah, it has to hold good fairly. Yeah. So and F1 until F2, that is recursively defined. Okay. So F1, F2 has to hold good fairly. Okay. At some point, and up to that point, every state on they must on that path, each state, the formula F1 has to hold good in a fair fashion. So as I said, the difference in semantics really, comes out of this thing. Fair semantics, Ex of P. It may not hold good in a state S, even if P is true in the next state. Since the definition is such that if there exists, the reason is if there exists no fair path at all from S, then it is false. There must exist a fair path, and on every fair path, that P must hold good in the next state. That's why that's one of the reasons why this differs. Similarly, AX of P can hold in S even if P is not true, because if there are no fair paths at all, then universal semantics, universal quantification semantics is always defined to be vacuously true. Okay? And that's why even if P is not true, under the fair semantics, AX of P can become true. Okay? Okay, so let's look at this one. Like this toy running example that we have been seeing. So in this, does EF of X of naught of P hold in S3 under the fairness constraint? F is equal, where F has this single constraint, P. So when I define the fairness constraint like this, what it means is that defines the fair paths. So fair paths are those on which P occurs infinitely often. All paths on which P does not occur infinitely often will be considered as unfair. So I'm asking the question, if EF of X of naught of P holds in S3 under this fairness assumption.
No, right?
Correct. Why?
Because there does not exist a fair path at all from S.
Exactly right. Okay.
But AFX will hold true, right?
That's right. So that's the thing, but I'm not included that. But so does EF of G of P hold I mean, fair, e.g. P hold fairly in S naught. If under the fairness constraint, if my fairness constraint is not P.
This is also not true.
So the only fair paths are P. So others are very silent. So others believe, oh, yeah, that's no. So I reveal the answer for this because that's the way thing. So look at this, EF of Q until not P. Let's assume that Q holds, although I haven't labeled in this figure, Q holds in S naught, S1, and S2. Q until not P, the question was, does it hold in S naught under the fairness assumption not P? It does, because so the path S0, S1, S2 followed by S3 continuously occurring, that path S0, S1, S2, S3 omega, that path is a fair path, correct? Because not P holds infinitely often on the path, and there this one is true, okay? Because that is a fair path originating from S0, S1, S2, as well as S3, because all of those they are paths, fair paths applicable to all those states, and that's the only fair path. There is another infinite path here. It's not S1, S2 omega, so but that is not a fair path. But it doesn't matter. But this requires that the property hold good only on fair paths, and therefore it is true under this fairness requirement. Okay, is that clear?
So are we the set of, like each of those set of fair states, we specifying them with a label, right? Or are we specifying them with a, like the explicit states?
No, I didn't understand your question. Can you
So,
repeat? Are we doing what?
so when we specifying a fairness condition for a Kripke structure, are we
Correct.
specifying a set of states which have to be visited infinitely often, or is the set of labels which have to be true infinitely often?
Yeah, but what I mean is when I say not a P, it is actually states. Okay?
Right. So we're meaning all states there in
When I
which not
do
a P
this
is true.
thing, I mean states in which not P is true. Okay? So I'm abusing the notation. I mean, yeah,
Right. Okay.
so that's right. So I'm using the set of states. It's actually the definition is states. Okay, it's because
Right.
path in a Kripke structure. But here, yeah, that's a good point. It's a subtle point. But yes, when I do P here, it is S0, S1, and S2. Okay, so it's really yes. So you should consider that a set of states. But I have kind of abused the notation here. Sorry. Yeah. So what I mean is all those states technically the definition of where is those are subsets of states in the Kripke structure. Here, I'm using that to denote P, set of all states such that P holds good. Here, set of all states such as not P holds. So this one is the singleton set S3, this fairness constraint, and the first fairness constraint has as its set S0, S1, S2. Okay? Correct, good point. So the important thing to notice is, so you need to do two things here. One is, of course, you will have to ensure that it is a fair path, that you have to restrict yourself to fair paths, and that can be implemented. I mean, usually that is more relevant when you do EG, because EG is one in which the satisfaction has to look at infinite paths, okay? And so that can be handled by restricting yourself to only identifying among those maximal SSC, you identify you keep only the subset of those strongly connected components that are fair, okay? And that is easy to check, okay, as per the criteria. And then you can restrict yourself to the thing. But additionally, since the definition of EX and CF1 and F2 requires, that you need to keep track of whether there exists a fair path at all from every state, okay, in checking. So those two things are important in understanding the modifications that you have to make for the model checking algorithm. So when you do check EG, you restrict checking only to fair SCCs, okay? So it's easy to identify fair SCCs. How? So you look at an SCC is fair, if you collect all the states from that and then see if its intersection with each of the PIs must be non-empty, okay? So that's easy to check. And then you, check EG that way. In order to ensure that the states that you check there exist fair paths originating from that, what we do is you add a special label, okay, for fairness for each state that is true if and only if there exists a fair path from that state. Now, whether that fairness label in a particular state is true or not, you can actually check by doing one pass, by checking with the EG algorithm, with EG true, okay? I'm sorry, yeah, EF of G is true, okay, yeah, see, with this modified, okay, thing. So, yeah, you will have to check this for fair SCCs, I should say. After you modify this to limiting yourself to SCCs, let me call this as check fair or something like that. So then you will have to do check fair of EG true for all the states. Then you label each of them, that determines the fair. And then when you check the EX of F and E of F1 until F2, you do that, and by wherever that you have F, you add the fairness label in that state that you will be that you'll be checking, okay, and that's what you do. So actually, there's a little small optimization that you can do. Since when you're checking like E1 until E2, you don't need to, you don't care about the label here, because if there exists a fair path from F2, the state in which F2 holds good, then the same path will also be there. There'll be automatically fair paths from all the states that lead into that thing. And that's why, you will sometimes see in books the algorithms not attaching this fair label to the first part of the F1. And so that's what you do, okay? So here, for example, when you check if Q if Q until not P fairly holds in state S naught under this fairness assumption, first you label when you run EG true, check fair on EG true, you have obviously all of them, the fairness label for each of these states, including S3, will be true, okay? And then you do this, okay? So if the fairness label were not true in a state, then of course this will end up being becoming false, and that's how you do. So EX also has to be done the same way. After conjoining the fairness label, whose truth value is determined by, and yeah, so that which states you label with the fair thing or not is determined by this phase there. Okay. So these are the two things that you that you will have to do in order to take care of fairness. Yeah. I hope that's clear. Any questions so far? I mean, this is part 1, and I'll be moving to part 2 now. This is the end of our discussion of explicit state model checking algorithm. The reason, although in the course I said we will be stressing on symbolic model checking algorithm, it is kind of important to understand this one in terms of the transition graph. You kind of this gives you a better intuition of what it means to model check, okay, before we move to looking at these procedures in a symbolic fashion. So any questions here? Okay, good. Let me move on. Okay, so first I will say in symbolic as a step towards symbolic model checking. So in symbolic model checking, so what is it? We as unlike in the explicit state model checking, so we'll be treating the initial state as a formula, transition relation as a formula, and the idea is to manipulate this formula in some ways to actually check these formulas. In this case, CTL formulas. So as a precursor, so as you know, the crux of doing symbolic model checking is to treat, define sets of states. I mean, interpret formulas as denoting a set of states for which the formula is true, set of states for which, where a state itself consists of some state variables. So those set of states defined by those state variables for which the formula is true. Therefore, so I want to start by looking at one of the simplest form of model checking. Model checking, what are called invariant properties, okay? Or just collecting, even the task of collecting the set of all states reachable from the initial state. First, I will show it as an algorithm manipulating sets of states, and you can always define a set of states by a formula that characterizes that set of states. Okay, so here's the idea. So this problem is the problem of collecting all the states that are reachable in one or more steps, starting from any one of the initial states of the Kripke model. Okay, so if you were trying to do this as collecting states, you can use this breadth first search algorithm. So this is the set of initial states. So then you say, what are the states that are reachable from any one of the initial states in one step? That you could compute as an image. Okay, you can so you take the image under the transition relation of the Kripke model, and then you add that to your initial state. That is, you union that with the initial state. And then image 2, and so on. So it's, you see, when you do it this way, it is more like breadth-first. In one step, you're accumulating a whole bunch of states, okay? And you're adding that. You keep doing that until you continue this, until the image at a particular step that you compute is, it doesn't add, okay? The union, when you add the union, it is the same state, okay? Or you can also check it if the new image is a subset of the collection of all the previous images. Okay. So this will be the idea, that essential idea that we'll be using for constructing symbolic model checking algorithms. The only thing is that you will figure out how to represent image and these initial states, etc. Some of which you already know how you could through the exercises that you have been doing as to how to represent them symbolically. Okay? So another way to look at this, okay, is that it is what you're doing is you're computing the smallest. By smallest, I mean in terms of the size of the sets. Okay, transitive closure R of T that includes the initial state. The smallest transitive closure R of T that includes, okay, which can actually be defined inductively as this, okay? So every state in I naught, R is a solution to these inductively defined rules. So every state in I must be included in R. And if S, for every S that is in R, and such that there exists a state TSS prime, then S prime will be included in this R as well. Yeah, and this is what? This one is showing a pictorial way, I mean, computing this transitive closure relation. And that's how these symbolic model checking algorithms you will see will be designed and devised. Any questions? Do you understand this? Okay. So here is a very simple thing. Okay, this when you collect. Okay, this only says collecting all the reachable states. So if you are interested in proving the simplest of temporal logic properties, remember that we had classified our properties as safety properties and liveness properties. An invariant property is a very special kind of safety property. I'm not sure if I defined it or not. It is really either AG of P, G of P, where P is atomic, is a predicate, not another, it doesn't have any CTL operators, it's a predicate. Okay? That, where P is a predicate on states, that is what is called as an invariant property. So in this sense, you don't need to, there's no nested formulas. Okay, there's only one temporal operator at the outermost level. And this kind of property, that is AG of P or G of P, if you're an LTL, or we can be checked by just collecting the reachable set of all reachable states. You compute the transitive closure, compute all the reachable states, and then you check if the negation of your property P is something that you expect to hold good. Not of P is what I call as the bad state. And what you have to do is to see that if the bad state is contained in any one of the reachable set of any of the reachable states. Okay. So the first part, this while loop is actually implementing the transitive closure. Okay. So you start from the empty set, and then you keep adding iteratively adding images of the previous the set on the previous step that you have accumulated. And at the end, when you have accumulated all of them, you can check if B intersection C is empty. If it is empty, then you know that no bad state is reachable, and you can say it is safe. If not, you have found an error trace to a bad state. Okay. Now you can see how this can be converted into a symbolic model checking formula, right? Because each of these states, you can represent them as formulas. Image can also be, you know, how to compute an image. If you had the existential operator, you can compute the image, and that's the idea. But let me stick to this state notation for some time before I move to the formula notation pretty soon. So this is not the smartest way to do, is it? Okay. You don't have to, if you really want to check G of P using this, you don't have to wait till the end to, until the end, until you exit the loop to actually check. Instead, you can move this check inside and see if at any point you, you know, you end up reaching a bad state. Okay, so that then, if so, then you can terminate it before you calculate or compute all the reachable states, and that's a more efficient. You can, so that you can prematurely terminate, and that's why what some people call as on-the-fly model checking. I had mentioned this even before with respect to explicit state model checking as well, where I said that, you know, you will have to do a on-the-fly model checking without actually constructing all the reachable state, and that's what you're doing here. Because even when in a lot of cases, even when the universe of states is huge, which can be exponential, the set of reachable states could be manageable. Okay. Therefore, so you do this. You're moving the check inside. You first check if the initial state itself contains a bad state, in which case you know that it does not safety properties violated. If not, then after you know, in each iteration you compute this thing. So there is another slight optimization that is done here. So you don't need to the previous you know, there you were computing the image of the entire set. So the result is that you keep computing repeatedly, redundantly computing images on already, you know, states that on which you have already computed. You can eliminate that by looking at what are called frontier sets. So you only you know, get the new set of new states that you have seen, that you have not seen earlier, and you know, keep that in F, and then you can compute the image only on that. Okay. The hope here is that maybe the formulas, when you're doing symbolic model checking, you usually you get you know, it's the space that you worry about. Okay, so you have to when you do explicit model checking, it's a space that goes haywire. So here, when you're doing symbolic model checking, the advantage is you have to get as much compression in the you try to get as much compression in the states, okay, as you can. The hope here is that maybe if you have smaller number of states, the symbolic representation for that is also small, but that is actually not necessarily sometimes true. Okay, so sometimes the symbolic representation of a large set of form, it can happen sometimes as well. But this is the idea used here is that. Okay, so a slight variation of that is. I mean, you can choose. You don't have to choose the smallest thing. I mean, you can choose anything. You know, you don't have to eliminate all the redundancy, as long as if there is a more compact symbolic representation of the thing, then you can do that. So these are just minor variations, interesting, that I thought that I'll also show you. Okay. Yeah, one point that I want to make is I showed when I showed in terms of sets, it is actually the transitive closure, smallest transitive closure of yeah. Yes. Yes, and the transitive closure, when you hit, is actually can be expressed as a fixed point of a suitably defined function. Okay, so viewing it that way is also sometimes is handy. Okay, so you can define these. So here, yes, this process of accumulating, you know, these, you're adding some things, some state. Each state can be, if you view that as being each iteration, the set of states being represented as a formula, then then what is each step doing? Each step is transforming that formula into another formula that represents a bigger state, one that includes the original set of states plus the image. Okay? And if that, what is done in each state, that computation of taking the image and adding it to an arbitrary state can be expressed as a predicate transformer. I call it a predicate transformer, and that's what is shown as tau here, okay? Designated as tau. If what is done in each of these steps on the right side can be considered as transforming a formula representing a set into another formula. That's a predicate, okay, which is a Boolean function. Each of these is a Boolean function, and what you're doing in each iteration is transforming that Boolean function. And that's what it is. I mean, you do that until you reach a fixed point of that function. So you can view that, the computing the transitive closure as as a fixed point of a higher order function. It's a higher order function because it is transforming formulas into another formula. So these are functions over formulas, functions over sets. Okay? So for example, so this is what I've shown here. I mean, there's a reason why it is called LFP, because it computes the fixed point, and it turns out in certain cases this is guaranteed to be the least fixed point, which is what we are looking for. Okay, so for example, so by defining the tau to be, tau is what happens in each iteration. Okay, this is a general pattern of computation that I want to identify. So the idea you'll see soon is that all CTL model checking of all the operators, CTL operators, each of them can be expressed as computing a fixed point of a suitably defined predicate transformer. In this case, the predicate transformer, for example, for computing the reachable set of states from an initial state, can be denoted by this predicate transformer. So it takes, given a formula X denoting a set, this is what it does. What it does is it takes the image of that X formula. So you have to, here I'll be interchangeably using formula sets of states, okay? So you'll have to, you should not get confused with that, because we are using that in a interchangeable fashion, okay? So X is actually a formula, and it happens to represent a state, a set of state. So what you're doing is, so you're computing each step at each point. I mean, you're computing the image of that, and then you're under what you have. What you have done is the previous thing. And the starting point is I. Okay? So you can start with this X to be false. This is one way of computing, okay? Where image of T of X itself is this formula. Okay. So what is an image of T under X, which is a set S? It is a set of all states. Yeah, it is the set of it is the it is the set of states that it's a collection of all the states that that every state belonging to X gets mapped to under T. And that's what image is. It can be expressed in this fashion. So it's a state which is in X which, so which gets back to S prime. So it is this, so S prime is included. This is a function over S prime, okay, formula over S prime, and S prime is in it. It is true if there exists some state in X which it is a image of under T, okay? So so with that tau, so you can see that so you can view this. So this thing is computing the symbolic formula, which are represented as sets here on the.
What is I?
I is the initial state, okay? The initial set of states. I is the formula that characterizes the initial set of states, S naught, okay? So the symbolic formula that it computes, it actually represents these states, okay? So false, you start with false, okay? If you invoke tau on false, what do you get? So image of false, the empty set is empty, and R is like a union when it on formulas, so you get I, okay? You're starting with false. As soon as you apply once the tau, you're getting I, okay? And then you start applying tau again, okay? So then you union I with the image of I, okay? The second iteration, what you do is you do image of I, you're computing the image of I, image of I, and then you're ORing that, and then you'll compute the image and so on and so on and so on, okay? This is what the formula will look like, okay? The symbolic formula actually returned, by this. And then you're checking, when does this terminate? When Q is equal to Q prime. So each time it is returned as the result of applying tau to an existing formula. So it terminates when you've reached a fixed point of tau. When at some point, when you do 2 tau of Qi to get Qi plus 1, that will be the same as tau of Qi. So so it is exactly the it's a fixed point of tau. Where a fixed point is of a function is something on which the return value is the same as the argument. So actually one can prove that this is one way of computing a fixed point, okay? And this reachability, like I said, the reachability algorithm can be expressed either as an inductive relation, like like I showed before, or as a fixed point of a function that maps sets of states to sets of states. Okay, so tau maps set of states to set of states as a fixed point. Actually, one can prove, as I was saying, this is the least fixed point of tau, as long as tau is monotonic. Okay, if tau is monotonic, then there is one very famous theorem by this guy, mathematician Tarski, which says that in the finite case, just monotonicity of tau is necessary and it's sufficient to guarantee that there exist fixed points for such monotonic functions, and the least fixed point is unique, and the least fixed point can be computed starting from, in this fashion, starting from false as a union of an infinite chain. Okay. Anyway, so we'll get to the theory later on, but right now I want you to understand the concepts, okay? And that it is important for you to understand this, that this process can be represented as computing the fixed point of a suitably defined predicate transformer. By predicate transformer, what I mean is that it transforms a formula representing a set to another set. And sometimes we denote, for convenience, this fixed point, what I have denoted as x hat here, as mu z of tau z. Okay. To show that it is the least fixed point. So any questions on this? Now there is a lot of symbols here for you to digest, but any questions? The example that you have on the assignment, although I have not said, one exercise that you can do on your own is to, actually one of you already asked as one of the questions, if he could use an existential quantification. Okay? Because I had shown you that the image can be represented as existential quantification. And we had already used fixed point there. Okay? So you can actually use that example to compute. I know it takes 5 iterations. Sometimes things, I mean, this gets a little bit messy beyond that thing, but I think 5 iterations are okay to actually compute see the, first in terms of image, okay, what the formula, the symbolic formula looks like. And so that can actually, it's actually a fixed point of the thing. The T itself, the transition relation, it's not a fixed point of the transition relation. See, in that example, in that sequential chord example, because there was a unique initial state. And therefore, what happened was, as you did T repeatedly, eventually for every initial state, you ended up ending up in an initial state, which looked like as though the fixed point was of T, the transition function. It's actually a function. Here, since we are could be starting with a set of initial states. That's why we are defining, you have to be collecting sets of states as you go along. And therefore, you will be, what you end up collecting eventually will be a fixed point of this transformer on sets. Okay, and you can start. I hope you start seeing the connection with CTL operators of the thing. So once I do this, of course, I'll have to, once I collect this. So what I get at the end is a symbolic formula. When I reach the fixed point, I get a symbolic formula that represents, that characterizes the set of all states that are reachable from the initial state. And then you can then do the intersection with the bad state, assuming you have a definition of what a bad state is, bad state in terms of formula. And the doing the intersection is checking if a conjunction is satisfiable. If the conjunction is satisfiable, then there is an error. Okay, but what I've shown here is only the calculating or computing the set of all reachable states expressed as a, in terms of fixed point of a higher order function that maps predicates, formulas representing states to another formula. Okay. So any questions?
So checking whether Q is equal to Q prime or not, that will require a call to some sat solver in this case, because we would have a formula to check to if two formulas are equivalent. That
Correct. So there's two steps here. Okay, there's one is this, this generating these formulas, right? Yeah.
yes, that is.
These formulas, so they are, yes. So eventually you, okay, checking if you have reached a fixed point, there you do need. Yeah. And after that, checking either you do on the fly or at the end, checking, some if you have violated the thing. So remember that the way that we define CTL model checking, we did, even in the explicit state, what we did was we collected all the set of all states that satisfied that formula. Okay.
Yeah.
And then did the checking. So here I'm showing, yeah. So yes, those are the two things. You mentioned one of the
Right.
things. The other thing is checking the fixed point also is requires sat solver or some boolean satisfiability checking. Yeah. The other observation is you can see how expensive this thing is. You have to, each step here requires existential quantification elimination. Okay? That's the most expensive part of this thing. Okay? You really want to compute formulas like this, you have to figure out a way of doing this existential quantification elimination on formulas as efficiently as you can. Okay? In this form, where the way I have shown it, actually sat solvers for doing this are not very, I mean, each time when you do existential quantification, as you know, there's a blow up. Okay? And we'll tell, under certain, certain kinds of transition system, there are ways to really very cleverly optimize that process, but still, worst case, the size will grow exponentially. But there are some very compact representations. SAT solver is one way to do it. There is something called BDDs, binary decision diagrams. Okay, and that's a compact way of representing formulas. And their existential quantification elimination procedure on, if you represent them as BDDs, can be done in this size linear of the size of the formula. Okay? Although the BDD itself can have a blow up in representations, that's why doing these through symbolically usually one uses BDD representations, the Boolean decision diagrams as they are called. For example, this is what new assembly has. That's, of course, there are lots of optimizations, etc., that are engineered into the system, but at the core level, it has a fixed point engine, okay, implemented in terms of BDD sometimes, or sometimes using SAT solvers. Yeah, so as I mentioned, CTL model checking can be expressed as calculation of fixed points of appropriately defined predicate transformers. We will see for each CTL operator, we define a predicate transformer. But the thing, I mean, it will be the structure of the algorithm is as shown here, which is parameterized with respect to the tau. It's the tau operator, I mean, that varies from one CTL operator to the next. Okay. I mean, even in the explicit state algorithm, you see that there was a fixed point thing. It's eventually it led to this SCC, right? I mean, so in some ways, the strongly connected components there were like some fixed point artifacts that you were actually reducing it to. Whereas here you are doing it directly on the formulas. The end game is computing fixed points of these tau.
Using BDDs will help us like optimize the Q not equal to Q prime check as well.
Yeah, but see, yes, no, but that check, you know, is
That will still be
even in SAT checks, it is
very expensive.
because that's just an implication check. Okay, a subset, whether something is subset or equal, is yeah, that can be done easily in SAT as well.
Okay.
Yeah. So that's why sometimes SAT is does so well when you even expand the thing out. That's why they kind of expand it out, okay, rather than eliminate the quantifier. Okay? But that has its own issue, okay, when you yeah. So that is one approach. Yeah. So let's take it step by step. Okay. So how exactly do you do this? How do you eliminate? How do you avoid maybe doing it without actually introducing existential quantification? So that's the SAT approach to model checking. The BDD approach, there you directly do the existential quantification. So this we already saw. So an instantiation of this generic algorithm for computing fixed points of a given predicate transformer can be instantiated for computing the set of reachable states from any given initial state by instantiating tau to be this. Okay, as we already saw. So it's the least fixed point of a tau that is defined this way. I union image of tau of z for any given z. So now we are getting, I'm going to illustrate to you for one of the operators of CTL. So let's do EX of f. So I'm using this notation, double brackets, with a CTL formula in it, inside it, to denote the set of states satisfying f. Okay, so this denotes the set of states. So what is EX of f? So that's what model checking algorithm does, right? So it computes this set of all states that satisfy a particular thing. Okay, that is the crux of the model checking algorithm. Of course, there is the additional, after that, you have to check if the initial state is inside it. I mean, that is now in symbolic formulas, it's just an implication check. So this does not require any fixed point computation because it is a one-step thing. All you need to do is, this is exactly this existentially quantified formula. It's the set of all states that map into something, map into a state that of all, yeah, where f holds good, okay, in one step. It's actually the image, okay, but image constrained in such a way in the next state that you're only looking at those things that satisfy f, the given formula f. Okay? So this can be computed without recourse to fixed point computation. Similarly, AX of f, although AX of f can be obtained by negating this, I'm just showing directly if you want to do it, how you would do it is AX of F is defined as this, yeah, here, as long as there exists one state, one successor state that satisfies F is good enough. Whereas here, it is insisting that every successor state should satisfy F, and that can be expressed using a universal quantifier. So for every S prime such that T is S of S prime, then F should be true in the next state. So which can also be expressed in terms of existential quantification that way. So here is the first instance of where I'm instantiating the fixed point calculating algorithm. Okay. So EF union F2 is the least fixed point of this transformer. So what do you do then? So you start with F2. So remember that how you did. So there's, I mean, sometimes it helps to look at the similarity of that thing. So you start first with states in which F2 is true. That's how you did in the labeling algorithm as well. And then you were adding, you're labeling those states from which there was a path leading, from that state to something that you already had. Okay, the beginning it is F2, and then you do that. Yeah, you take the union of that. Okay, so if there is an F1, if there is a state in which F1 holds good and there exists in one of its successor state leads to something that you already had, that you already have accumulated, then you add that. Okay, this is what is happening in each step, and you keep doing this. Okay, then until you reach a fixed point. Okay. You kind of show this pictorial. You can draw a picture. Okay. So unfortunately, I don't have for this thing. Maybe you can do it yourself to explicate. You start with set of all states, a circle with that includes all the states that satisfy F2. And then you expand that. And to that, you add all those states that are in which F1 holds, and there exists in one step, you can reach a state in F2. And then you add something which you can reach it in two steps and so on. But then you do that, when you do this symbolically, you're doing it, you're accumulating all the states. In each step, you're accumulating all the states that go into that thing in so many steps. Okay, so that's why this algorithm is a breadth first. It has the effect of breadth first, doing it in a breadth first fashion. So sometimes, depending upon the transition relation, the number of iterations that you require here to reach fixed point can actually be much, much smaller than in the explicit state model checking algorithm, where you enumerate each states. Okay, so in one step you could have done. I guess there are some optimizations that you can do there as well, so that you eliminate states that you've already seen. But nonetheless, this is a breadth first kind of a thing. So EX is already defined here, and that's what I'm assuming that I'm using here. So draw a picture. So one exercise that you can do is draw a picture of this. So to see what happens, what are the states, the set in terms of concentric circles, where each circle denotes a set of states. with the smallest one denoting the set of states that satisfy F2, and then it'll be clear for you how those iterations lead to a fixed point of tau, which will end up exactly containing the set of states that satisfy E F1 union F2. Yeah. So in this case, you're starting from false, and then you are applying, repeatedly a tau until you reach a fixed point. Yeah. So sometimes it is convenient. This is not the only way to think. So first of all, let me ask you a question. So I keep saying the least fixed point. Okay. So for any function, for any arbitrary function, there are multiple fixed points. But there's one value, set of states, by value I mean, there is always a fixed point of any predicate transformer. So can you believe that okay, do you first agree that there can be multiple fixed points? If so, give me one fixed point that is the fixed point of all taus. That's a trivial solution for this, okay? So just consider the set of all states, so set of all universe of states. Since tau is monotonic, okay, I'm assuming tau to be monotonic. True, the formula true, which represents every state in the universe, is always a fixed point for any predicate, monotonic predicate transforms, right? Because you always, tau of true is true. So you could see, actually, the intuition is if you start with different, initial states, you get, different fixed points. Okay, and the idea, but here we start with false. Okay, and embed initial state inside it, and that's why you get by starting with false, you get the least fixed point. So there are multiple fixed points, okay, and they're all yeah. So the first thing that you will have to be comfortable with and convinced is by asking these kinds of questions. Okay, there are multiple fixed points. If so, what are those? Okay, and that's why So then yes, so you don't want to avoid trivial fixed points. Okay, and therefore, and this is a standard way to compute to get to that least fixed point that has that, which is what you're aiming at when you're computing it this way. Okay, maybe I'll stop here. So there are also this thing, sometimes there's this notion of greatest fixed points. It's not the only way to compute fixed points. And there's another way where you start from true and then go down, okay? Now go down the chain. So here you're going up the chain from false to the fixed point. You can also go down, and that gives you what I call greatest fixed points. And you will need that as well to express some operators, but I will do it next time. So I will stop here and take any questions that you might have. Any questions? Okay. Yeah, I'll stop here. See you Wednesday. Just a heads up that I think the second assignment will be going sometime this week. So you should submit your assignment today if you haven't already. Thank you. Bye.